In this paper, we present logic network flow, a novel optimization formulation that transforms temporal logic specifications into network flow constraints, achieving tighter convex relaxations and computational speedups for robot task and motion planning. Motion planning algorithms typically assume predefined goal states. However, many robotic applications require handling logic-constrained, time-critical tasks. For example, not phi 2 until phi 1 specifies that the robot must first obtain a key before accessing a room. Temporal logic specifications provide the formal framework for encoding such complex requirements. However, temporal logic-constrained motion planning faces significant computational challenges. While LTL specifications mostly use automata-based methods, the automata size grows exponentially with specification complexity. MTL and STL specifications typically use optimization-based approaches through mixed integer programming for better scalability. Nevertheless, these formulations still require prohibitive solving times. To mitigate the computational bottleneck, we introduce Logic Network Flow, LNF, a novel optimization formulation that achieves tighter convex relaxations to improve solving speed. The key innovation lies in placing predicates on edges of a network flow graph instead of on leaf nodes of a tree, then using flow conservation constraints to couple them across branches. This leads to provably tighter convex relaxations than traditional logic tree formulations. The LNF framework is integrated with piecewise affine dynamics, providing a complete task and motion planning formulation across diverse robotic tasks. Inspired by the graph of convex sets formulation, LNF introduces binary edge variables YE and multidimensional continuous flows omega E on each edge of the network graph. The vector Z pi represents atomic predicates as input flow entering the network, traversing from source vertex Vs to target vertex Vt. When an edge is traversed, that is, YE equals 1, its flow must satisfy convex set constraints that use indicator vectors V plus and V minus to enforce which predicates must be true or false on that edge. When YE equals 0, the edge is not traversed by the flow. To maintain logical consistency, all predicates on that edge cannot simultaneously be satisfied. Flow conservation constraints at source and all other vertices ensure consistent propagation of flow through the network. LNF builds on the graph of convex sets backbone, which yields tighter convex relaxations. However, this comes at a cost of introducing a large number of continuous flow variables omega E that can offset the solving speed gains. Our solution is a network flow-based Fourier-Motzkin elimination procedure. We systematically eliminate all flow variables, replacing them with inequality constraints between the predicate variables Z pi and edge variables YE. Crucially, this transformation preserves the exact same convex relaxation tightness. We get the benefits of GCS without the variable overhead. Starting from the source vertex, we apply the Fourier-Motzkin elimination scheme. We combine flow conservation constraints with convex set constraints to generate valid inequalities directly between the predicate variables Z pi and edge variables YE, effectively projecting the formulation onto a lower dimensional space with the flow variables omega E eliminated. We propagate this Fourier-Motzkin scheme vertex by vertex downstream through the network structure until reaching the target vertex. For the common conjunctive-disjunctive form, after applying Fourier-Motzkin elimination, we arrive at the simplified LNF formulation shown on the right, which provably gives tighter convex relaxations than the traditional logic tree formulation shown on the left for comparison. The key to tighter convex relaxation lies in the valid inequalities generated by flow conservation, which couples the predicates across different branches of the network flow. These inequalities are equivalent to the logic tree constraints when variables take binary values, but define a smaller feasible region under convex relaxation. To demonstrate broader applicability, we apply our Fourier-Motzkin procedure to the minimum time linear control problem with double integrator dynamics, a benchmark used by graph of convex sets. Starting from the GCS formulation, we apply the same elimination scheme to remove flow variables. The result is the baseline formulation augmented with several valid inequalities that tightens the formulation, as indicated on the slide. Despite having applicability limitations, our proposed Fourier-Motzkin elimination has clear advantages. First, Fourier-Motzkin elimination reveals the mathematical structure underlying GCS's tighter convex relaxations. For the previous two problems, the elimination shows that GCS equals the baseline formulation plus tightening valid inequalities. This simplification makes proving tighter relaxation than the baseline almost trivial. Second, Fourier-Motzkin elimination provides significant computational performance gains. For the previous two problems, the simplification increases solving speed over the original GCS formulation, with improvements ranging from several times to orders of magnitude faster. In addition, Fourier-Motzkin elimination allows users to selectively exclude some valid inequalities to balance between tighter relaxations and smaller problem sizes. Removing continuous flow variables can also reduce RAM usage, benefiting solving of larger problems on resource-constrained hardware. Logic network flow integrates with dynamics formulations to form a complete task and motion planning framework. In this paper, we present comprehensive piecewise affine PWA dynamics formulations, giving users a flexible toolbox to model different robotic systems. Dynamic network flow is a special case of PWA systems that switches between points in discrete state spaces. It begins by modeling discrete state spaces using temporal graphs, then expands them along the time horizon. Edge traversals serve as binary predicates, while conflict set constraints enforce collision avoidance for multi-robot coordination. For continuous systems, we present Big M formulation for general PWA dynamics. Other formulations such as convex hole and Bezier curves also exist. The binary predicate vector Z-pi is shared between the logic and dynamics formulations, coupling them to ensure dynamics evolve according to logic constraints. We evaluate logic network flow on temporal graph navigation using dynamic network flow for both single and multi-robot scenarios. Test environments include grid worlds and road networks with random edge costs modeling traversal difficulty. We evaluate three task types: multi-target navigation, requiring the robot to visit at least one target within each target group while avoiding obstacles, vehicle routing problems, where robots serve customers within specified time windows, and sequential tasks enforcing ordering constraints between customer visits. First, we investigate a multi-target path planning experiment, where a single robot must visit at least one target from each of several target groups while avoiding obstacles in a 16x16 grid world. We benchmark our logic network flow formulation against the logic tree approach established by Kurtz and Lin in 2021. Our proposed LNF formulation tightens the root relaxation gaps from 31 to 66% down to 10 to 52%. The tighter relaxation results in 2 times speed up for 2 to 3 target groups and 3 times speed up for 5 target groups. We next evaluate our approach on vehicle routing problems with time windows, a classic optimization challenge where a fleet of robots must visit task locations within designated time windows. We test 100 problem instances with random traversal costs on simulated road networks containing up to 182 vertices and 534 edges. Our LNF formulation dramatically tightens the root relaxation gaps from 31 to 38% for LT formulations down to just 7 to 8%. This significant improvement in relaxation tightness translates to computational performance. For 3 robots serving 9 tasks, LNF achieves a 31 times speed up, improving global optimality. When scaling to 6 robots and 18 tasks, LNF maintains over 13 times speed up, while the LT formulation times out without finding the global optimal solution. We also evaluate a more complex variant of vehicle routing problems, where robots must satisfy sequential dependencies between tasks. In this scenario, certain locations cannot be accessed until other robots have reached a prerequisite location. We test 100 problem instances with these ordering constraints on the same road networks. Our logic network flow formulation tightens the root relaxation gaps from 37 to 40% for logic trees down to 17 to 18%. While the sequential dependencies make the problem more challenging, LNF still achieves an 8 times speed up, improving global optimality for 3 robots with 9 tasks. When scaling to 6 robots and 18 tasks, LNF maintains over 6 times speed up, with the logic tree formulation again timing out. In this experiment, we demonstrate LNF's capability to coordinate 3 bipedal robots in a disaster response scenario. The robots must quickly find optimal paths to complete time-critical missions, rescuing survivors from a crashed airplane, retrieving equipment from factories, and extinguishing fires, all specified by temporal logic constraints. The optimization minimizes both the risk of falling from rough terrain and the risk of overheating nearby the fire zones. In this slide, we see the visualized optimal trajectories computed by LNF. The planned paths for the 3 robots are shown in blue, green, and orange, navigating around obstacles shown as gray circles. The varying background colors indicate terrain roughness, with lighter regions representing higher fall risk. Red stars mark the task locations, including the crashed airplane, factories, and fire zones. Notice how the planner optimally assigns robots to different tasks based on terrain and temperature conditions, coordinating their movements to complete all missions while minimizing the chance of failure. For the 2 terrains shown above, Our LNF formulation achieves 4 to 40 times speed up compared to the LT formulation. This dramatic improvement, driven by LNF's tighter convex relaxations of 58 to 68% versus over 90% for logic trees, enables rapid mission planning critical for time-sensitive disaster response. We also demonstrate the planned trajectories in a MuJoCo simulation environment where the bipedal robots use A-leap-based controllers with PI guidance to track the optimized paths. This visualization shows the feasibility of executing the computed trajectories on bipedal robotic systems. In this experiment, we evaluate logic network flow on robot motion planning with point mass dynamics. Test environments are two-dimensional workspaces decomposed into 8 to 15 safe convex regions for collision avoidance using the Big M formulation. The robot must navigate through safe convex regions to reach 4 to 6 targets arranged in sequential pairs. The robot must visit the prerequisite targets, but can then choose which subsequent target to visit following the prerequisite target. We evaluate point mass navigation inside two environments for 100 problems with randomly sampled target reaching costs. Our LNF formulation tightens the root relaxation gaps from 41 to 57% for LT formulations, down to 37 to 54%. In environment 1, with 8 regions and 4 targets, LNF achieves 3 times speed up, winning 44 out of 50 trials. In the more complex environment 2, with 15 regions and 6 targets, LNF maintains 2.5 times speed up, outperforming LT in 36 of 50 trials. In this experiment, we test LNF's capability on bipedal locomotion planning with linear inverted pendulum dynamics. The robot must plan kinematically feasible footsteps to visit at least one target from each of 5 groups, while ensuring all foot contacts are placed within designated safe regions. The simulation shows the robot successfully navigating through the workspace, placing footsteps only in safe regions, while visiting all required targets. This capability is essential for domestic robots that must carefully step around scattered objects on the floor. In this experiment, we deploy 3 quadrupedal robots that must deliver color-matched pairs of objects to assembly stations with sequencing requirements. Plates before cubes at each station. The narrow T-junction creates a coordination challenge where robots must schedule their passage to avoid collisions. This animation shows the 3 robots, denoted by yellow, green, and magenta dots, executing their planned shortest collision-free paths that satisfy the temporal logic specifications, ensuring all color-matched objects are delivered to rooms H, I, J, and K in the correct sequence. In this experiment, we demonstrate LNF's real-time replanning capabilities by having a quadrupedal robot guide a human to one of 3 potential destinations subject to unexpected disturbances, including the human physically pulling the robot or obstacles suddenly appearing in the planned path. This video shows the robot executing the planned path in real time. The top left diagram displays the continuously updating trajectory, with the yellow stars marking the 3 potential targets. Watch how the path instantly adjusts when the human drags the robot backward or when obstacles are detected, demonstrating LNF's ability to replan in response to disturbances.